So let's make some notations here. We have v of x from our D to a set. So it takes parameters in D dimensions and it gives us a set. So this set is closed, smooth boundaries. So let me right away define the notation for the boundary. B of x I will call. So this is the boundary of B of x. So what is the next definition? Let me define the graph right away. So this graph is going to be a set of points x and y, such that when you take a parameter x, y is going to be on the boundary. So here, let's make a little y here now on the boundary of the set. So x is in our D and y is in the boundary. And what is the next definition? We want to also define the normal direction. So this is going to be the unit normal outward vector n of xy. So let's write it down. This takes values on this graph G, and then it gives the and it is the unit normal vector. So what is next? Next, we want to define the derivatives, the intrinsic derivatives. Maybe not squeeze here. Let's define it here. Intrinsic derivatives of what? Of the function, let's say f of xy from this graph to real numbers. So to define these intrinsic derivatives, we want to define what's going on when we perturb the x. And in that case, we cannot fix the y. Y is on the boundary. And as we perturb the x, it's not going to be on the boundary. So what we want to do is, if you are looking closely to y, so let's say this is vd of 0, and this is v boundary at a nearby x. So we want to define these curves from the point y to, I will use this notation. So I will not explicitly define these curves, but these curves are smooth curves. When x is equal to 0, in this case, it's equal to y, and it follows the boundary on the, as you perturb the x. So you shift the surface a little bit, you perturb the surface, and you move from y to v of xy. So now, once we have these smooth curves on the surface, we can now define the derivatives here, the intrinsic ones. So let's make a definition. Let's make it at 0. So I want the x here. So this is epsilon, this is e epsilon 0 y divided by epsilon. So this is the usual epsilon definition. So we are at the 0 y point, and then we move a little bit an epsilon.
Does definition depend on the choice of the curve, right?
Yes, but we fix a particular curve here. So we define a unique curve. So I'm not defining it explicitly, but this curve is the curve actually that follows the
notation of the derivative should somehow depend on the curve.
No, because okay, so let me explain it like this. When you have any curve like this, there are two, you can decompose it into normal direction and speed in the tangential direction, speed that is tangent to the surface. And this curve is the unique curve that there's no speed in the tangent direction. So it's like locally the shortest curve in a sense. So this is actually unique, and then we don't need an extra notation.
So you have to define this curve specifically so that it's unique.
Yes. We define it, but I don't want to spend time on that one. So let me give a straightforward example here. Dx of ny. So we have talked about this, defined at least the normal direction. Now we can talk about the x derivative of the normal. And this is going to play a role in its formula. Next, I want to define the derivative. This is for any function f on the graph of this v. Now I want to define the derivative of this function itself, v of xy. How do I do that? Let's make one more thing here. One more definition. So we define the derivative, intrinsic derivative of v as the derivative of the identity function on the surface. So this y is f of xy is equal to y on the boundary. So we are taking the identity mapping on the boundary, and we are taking the derivative of this map. And we simply set the derivative, first order derivative, to be equal to dx of y. And once we have done this, now this derivative is a function on the graph, right? It takes values for each parameter x, and for each point y on the boundary, it takes a value. So now we can further introduce the second order derivatives. So okay, any question up to this point? So we have defined now the first order and second order derivatives for our set valued function b.
So the question, the partial x parenthesis y, does that mean it does not depend on x anymore?
No, it's not really like that, because again, when you're taking the x derivative of this function f of xy, when you perturb the x, you cannot fix the y. So y has to still follow this curve.
Is it a notation? The second part is the new notation you introduce?
Second part,
Is the partial x, y?
This is the notation, this is definition. Maybe let me put it like this. And this is also a definition.
I think the chance question is what does partial x parenthesis
Yeah.
y means?
Oh, that is, oh, let me maybe put it here. This. So again, I'm looking at the functions f, which takes values for each x. The y is on the boundary. And now for these functions, I have defined the derivatives like this. And now I'm taking this function f of xy to be equal to y. And this is exactly the identity mapping of the surface, the boundary itself. So now I'm defining dxb as the derivative of the identity mapping on the surface.
So the y for the first derivative and the second derivative are the same,
Are this
uniquely determined by x,
yes.
because it's not like the derivative with respect to measures that you have extra, or every time you make a derivative, you have extra variable.
No.
The y is this variable on the boundary.
Yes. No.
So it's always associated to the x uniquely. Right?
Yes. There's no problem. Yes. So now, if there's no questions, let me move on to the motivation a little bit. So why you might want to interest in some objects like this. So the thing is, for example, I will talk about the mean variance problem. It's essentially a two-dimensional problem. You're trying to maximize the expectation while trying to, at the same time, minimize the variance, for example. So in that case, what we usually do is we take a weighting of these two things and then we project it into one dimension. But what is happening at that transformation is we kind of lose the time consistency. And when I mean time consistency, I will write down what I mean. But it means when you solve the question from now to the future, from time 0 to time t, and then you move in the time, like you get into a middle time, little t, your optimal control might not be optimal at that little t. So that's kind of the time inconsistency in that case. So when we project this two-dimensional problem into one dimension, we have this problem of time inconsistency. Well, that problem might be, by the way, important in a sense that sometimes you want to commit that control from 0 all the way to capital T, but that's not our interest here. So you can also think about like not only two dimensions, but n-dimensional problems in a sense that, for example, let's say you have a portfolio of assets, a lot of assets, and let's say it's big, then you cannot just take the market values of everything and then project it into dollar amounts. There are problems with that, like you have a huge liquidation costs, you cannot immediately liquidate all your portfolio, or there are transaction costs going on. So just projecting it into one dimension might not be always the best strategy, at least. So one approach might be just keep the dynamics in n dimensions and then approach the problem in n dimensions, and then at the end of the day, reduce it to one dimensions. That's probably one approach. The other thing we want to consider is the game problem. So we want to get into the game at the end of the day, not in this talk, but hopefully in the future works. So in games, usually there are multiple equilibriums. There's no unique equilibrium. And we have defined also, there are some works with my advisor too, that for n-player games and mean field games, we consider the, for n-player games, not me, set values for games. So we look at all the values corresponding to all equilibrias, and that set value actually satisfies the time consistency. So if you can get the Ito formula in the set valued settings, and potentially you get the master equation, the related PDE in the game literature, at least heuristically at this level. We are not there yet, but that's our hope in the future. It's a great motivation for the future work. Let me also mention the talk that was given by Professor Charan Ararat has some similar interests in mind, similar motivations. So let me define the control setting here, because I will need it a lot, and then I will get into some examples. Let's see how it's going. So we have the Tx alpha. This is our state process starting from time t with the state x and using the control alpha. So it starts at x and it's an ST. I cannot use S, right? So it's R, Tx. It's R. So it's an ST with drift and a martingale term, and then we have a value associated with this, which is forward in this case, and we have a backward value, Tx alpha S, and we have the terminal cost G. And this is the BSD with the terminal cost capital G. This is different from the graph. The terminal cost, the capital G, and we have the running cost F. And this
If it's different, why don't you use a different notation? Why do you want to confuse the people? Use the
because
same notation?
so
There's no line. It's.
yeah,
One has a line.
Without a line, okay.
yeah. If I use like small g, then I want to use small f, but I use the small f here. So I was like, why not keep it capital G? I don't think that.
You can use this more, how to say.
Not the script.
Normal
Not
capital.
Cursive.
This is my normal capital G.
Standard G.
This
Capital
is,
G.
this is his standard G.
Oh, okay.
Yeah. He can't write this. He can't write it. He didn't learn this.
Okay, so yeah.
That the script G is.
So, okay, this is the value associated with this control alpha, and I want to define my set value in this control setting right away. So t and x. So when you start from time t with state x, I want to essentially collect all the controls, all the values, sorry, for all the controls. Okay, so I take a look at all the controls and I'm collecting all the values associated with them into one single set. Now let me also mention about what do we mean by optimization in 1 and 2 dimension. I will try to squeeze it here. In 1 dimension, in 1 dimension, this set looks like this. So it's an interval. There's a values that you can achieve, and there's a supremum here and an infimum of this set. And we can take a look at it as the supremum is the optimal value in this direction, and the infimum is kind of the optimal in this direction. So these are the boundaries here. And in higher dimensions, so instead of this now, we have a set, let's say in 2 dimension, and we can say, hey, this point is optimal now in this direction. Now we have more flexibility here in a sense that we have a huge boundary now, not only 2 points that we can kind of call as an optimal. Okay, now, do I miss to say something? Okay, I want to now go into the mean field, so let's.
I have a question.
Yes.
So what does intrinsic derivative look like in 1D?
In 1D, it is just whatever the derivative here. Like if you just follow this single point, let's say, let's forget about all of the set, but just focus on the single point, then however it moves smoothly. And whatever the derivative of this is, that's the derivative.
So the usual derivative.
Yeah. It matches with that, yes. So I also want to mention maybe at this point, the Hamilton-Jacobi-Bellman equation that I will mention for higher dimensions, when you set m is equal to 1, it is immediately reduces back to the standard Hamilton-Jacobi-Bellman equations. Yes.
It is trivial that your VTX is closed and have smooth boundary.
No, I'm assuming, okay, so let's put here a closure. So I wanna close it right away. And for the smooth boundaries, no, typically, actually the answer is not true. So in this talk, we assume it is smooth and we are interested in the classical solutions. But of course, one very interesting question is to extend these regularities to less regular structures, but that's for the future work right now.
Is this for fixed omega or is it a subset of LP?
No, this is no, this is just a single point. Now at the small time t, the filtration is just a single point. So this is also a single value. So there's a single value associated.
Okay.
So for example, maybe very straightforward the example is you can get, if you choose like, Okay, I cannot do it right away, but you can make it essentially a ball, for example. You can arrange the parameters in a way that at the end of the day, VTX is just a ball, maybe with a center, for example, 0 and x. It moves to the right, left, or you can arrange it in a way it's like extending the ball. Like just to have simple examples in mind, you can achieve something like this. So now as a motivation, let me move on to mean variance problem. Motivation. So what is the question here? Supremum over alpha. And I want to consider the expected at the terminal for this dynamics. So I'm trying to maximize this while I'm also trying to minimize the variance. So let me maybe not use double bars here. Now I want to introduce two things. So again, so here is the variance term. So I'm trying to minimize this while maximizing this, and I'm reducing the question into one dimension right now. But in our settings, let's define the VTX. So to do that, let me define the y1 as xt tx alpha minus. I'm reducing the notations a little bit, but now we can define the y1 and y2 corresponding to the expected of x and expected of x squared. Now we are looking at the set VTX, which is collection of all these y1 and y2. Now it's two-dimensional. And we can rewrite this problem of supremum from the initial time capital T as now we can take the supremum over all the values in our set. Once we have collected this V1s and V2s of phi of phi, phi of y1, y2, for the expected we have y1, and then minus lambda over 2 y2, and then plus lambda over 2 y1 squared.
Excuse me,
Yes.
can you explain one more time for the VTX? Why is there like a set of value instead of set of the random variables, like for the VTX?
Here?
Yeah, oh, you fix omega? Yeah, that's.
No, I don't fix omega. So y, so this PSD is essentially adapted to the filtration. And when time, this S is equal to the small time t, the filtration is 3. So this is just a single value at this moment.
I see, thank you.
Like here, it is expected, for example. When this is, the notations are not good here, it's going to be corresponding to the expected. So now what do we gain? Again, I will get into the application. Now we are at the stage of motivation right now. We can rewrite this supremum problem in this way. And what do we gain by doing this is we have the time consistency for this problem, for our set value VTX right now. But this problem here might not be time consistent. And while I'm talking about the application right now, I will mention a little bit more. And it's called the moving scalarization. And in this case, phi of y is linear in a sense that there's a weighting lambda so that it is lambda dot with y.
Yeah, you may want to use a different notation, because I just use a lambda for different purpose.
I've used it for what? Oh, well, it's also a weighting, right? So, yeah.
That lambda is a vector.
Is it better now? I hope it's better. Okay. Okay, I want to talk about the time consistency in this case. So supremum over alpha. Now we have this problem lambda dot y and then t x alpha. Let's say alpha star is up. Let's say we are looking at this problem. We have this multidimensional y, and we are weighting it with lambda, or taking a direction lambda and projecting it. And we are looking at the supremum over alpha. And let's say we have an optimal control alpha star, and the time inconsistency means this alpha star might not be optimal. Let's write it down. Well, I should write probably essential supremum. So let's write it like this. How about let's put a zeros here. So this question is from time 0. I don't want to introduce too much functions. T, x, t, and 0, x, alpha star. But I don't want to spend more. I will not write that. So alpha star is optimal doesn't imply that alpha star is going to be still optimal in the future time. So initially we were looking at the time 0. Now we are looking at time t in the middle. And for the first part from 0 to t, we are going with the dynamics of alpha star. And then later on, we are again solving the problem of taking the supremum over alpha. So we are optimizing it again in the middle time, and our initial problem of optimal control might not stay optimal here. But there's a so-called moving scalarization, or the dynamic utility. So it might be optimal, and it is optimal for well, it might not be optimal for a fixed lambda, but if you allow this lambda to be a process, and this process at time 0 is equal to lambda, then this alpha star is optimal for this problem. Now we allow this lambda to change in time. Or in a sense, you can look at it like this. When you solve your optimal question, optimal control alpha star, you know that now since we can construct alpha, and I will talk about it at the end when I present the Hamilton-Jacobi-Bellman equation. So this is the application for our work here. So once we have this lambda, what you know is your alpha star, although initially you want it to be optimal for the weighting alpha, it is going to be optimal for this lambda, whatever you are computing as this lambda. So if you are okay to use this alpha star initially, then you know that it is going to be optimal in this weighting in the future. So you can compute this x at the future time, and then you can decide if you really want to use that control in a sense, because you know that it's going to be optimal for this weight. Any questions here? Okay, maybe I can squeeze something here with the hopes not erasing the board. Let's see. So I want to talk a little bit about not too much surface evolution questions. Okay, so there's a large literature on what's so-called the surface evolution equations, and what it looks like is there's a time derivative in our notations I'm writing. So it's now only depending on time t, and there's a set here, and we are looking at the first order derivative, and this is given by some function depending on y on the boundary, well, t initially, let's say, t the time, the y on the boundary, then there has to be a y, right? And n and dy of them. So the normal direction and the derivative of the normal direction. So these are very well studied, and one example that I should mention is the mean curvature flows. So in the beginning of 1990s, there's a huge literature here, a lot of contributions. And then in the beginnings of 2000s, there's a work relating the stochastic target problems where you're trying to drift this process into a target. There's also a set value defined for that, and these are connected with the mean curvature flows. And what else do I want to say? Surface evolution. Oh, so the difference is here, there's only one time parameter t. In our case, we are relaxing that and we are kind of generalizing it into d dimensions. And here it's the first order ordinary differential equations, and we are generalizing it into two-dimensional second order partial differential equations. And as for the applications, these usually are going forward in time, but for our applications, since we are interested in values, we have backward. The terminal is given for us.
Maybe in these applications, how do you guarantee the smooth boundary condition on V?
It's usually not smooth. Yes, it's usually not smooth. It's hard to guarantee. And well, there's also a notion of classical solution here, also a notion of viscosity solutions. But in our work, we don't have the viscosity solutions yet. These are depending on some geometric properties of this equation. But we don't have these tools yet, so it's a future work for us. But we cannot right away guarantee both the smoothness in Tx and the smoothness of the surface. It's not very easy, actually. Right now, we are not worried about the regularities and try to move on. Okay, so finally, let me move on to the Ito formula. So let's say everything is smooth. No worries about that. Sorry again for using exactly the same notation. This V is not the same V as there, but serves the kind of the similar purpose. So I hope it's not confusing.
The reason I can distinguish is different.
Really?
I can see it's different.
Okay, that's well, okay, that's good. Let's see. So let's write down the usual Ito formula. So let me put that here. 1 out dx v, and then we have correction terms going on. Yes. Minus yes plus. Okay, I have to erase the word anyway. So let's see. So let me write down the maybe. What does it look like? Okay, I'm writing it for when the dynamics are the Brownian motion. So this part is the usual Ito formula that we know. So dt of v. Now we are considering the derivatives of the set valued function that we have defined. So we are starting from an initial point on the boundary y, and we are following this dynamics from the Ito formula, dtv, dxxv, and dxv. The only extra term here is this term zeta, which lies in the tangent space. So we are generalizing here the motion on the surface. So you can choose a direction to go. And since it is in the martingale term, there's a corresponding correction term here. And the result says, let's consider, oh, this has to be boundary. And this has to be boundary. And the result says, let's also make a little plot here. And so we are starting from the time 0. We take a y on the boundary of the set value at time 0, and we move forward with the Ito dynamics, which is a little bit more generalized to consider the surface moves. And at the end of the day, at time t, we can describe this boundary with the Ito formula starting from this boundary. So in that sense, it is the usual Ito formula that we know. Any question about the structure here? So, cool. So,
Is there anything to say about the K?
oh, yes, actually, thank you very much. So I mentioned here, the xn plays a role in Ito's formula, so it's not visible there, but actually this correction term has dxn and dyn in it. So it plays a role. This correction term contains a term with dxn, the x derivative of n, and a y derivative of n. Y derivative is the usual derivative on the manifold. There's no new thing here. It's the intrinsic derivative on the manifold. So it also contains the new definition of dxn. Yes.
Maybe you already said this and I missed, but going back to the definition of B, its domain is RD and it's set valued, but where does that set lie? Still in RD?
Perfect. Sorry, I missed it writing that down. This lies in Rm. Any m-dimension finite. Yeah, I should have said this before. Sorry.
I was a little confused by your derivative because f is a function of x, right?
Yes.
X is an RD,
Yes.
but then you have f epsilon. Epsilon.
Yes. Yes. Okay. So for the notations also in the Ito formula, I'm writing everything for d is equal to 1.
Oh,
Because otherwise the notations gets really messy to keep track of traces and stuff. I just reduce it everything to 1 dimensions. Here also, like I'm taking R, this N is actually in Rm, so you do it component wise. So yeah, I'm reducing the notation. Yes, sorry. So let me not miss anything. Okay, now I want to continue with the time consistency in our setting. So now I'm in this control setting that I've defined here, and I'm interested in VTX. So let's write down the time consistency for this problem VTX. Can I squeeze it together? This is 0. Hopefully that's better. So what do we have here? On the left-hand side, we have our original set value, b of 0x, starting at time 0. And on the right-hand side, what do we have? We have this value. Now, again, we have the parameters 0x alpha. This is where it starts. But now we have two extra parameters where it ends at delta with the terminal cost phi. So this is exactly looks like this. However, it ends at the smaller time, let's say t plus delta, and with the terminal cost phi. So this is this definition here. So what are we looking at here? Again, we are considering all the controls alpha, and we are looking at the phi's. Now phi's are coming from this set b of delta x delta. So in a sense, you are looking at the 0 to capital time t question, and then you say, hey, let me look at the middle time t, and then let's solve the control problem from here to here, from small time t all the way up to capital time t. This is this set here. And now I want to use these values as my terminal values in the middle time, and I want to solve it again from 0 to small t, which is this part. And this is consistent with solving the problem from initial time 0 all the way to capital time t. So this is the time consistency for our set valued function. And it's kind of robust. It appears in the stochastic target problems, mean field games, and player games. You can formulate your question in set valued formulation, and the corresponding time consistency is kind of robust. It's satisfied in many cases, not all. And finally, let me introduce the Hamilton-Jacobi-Bellman equation. Let's see where can I squeeze that in. Okay. XV, and then I have this F. Oh, I forgot. Well, this is much smaller. Can everyone read it? Is it okay?
I'm pretty sure Peter cannot read it.
Yeah, let me write it here. Yeah. Okay, sorry. I'll drop the line. And let me shorten it. Took this on. Okay, so this part of the question, this looks like the Hamilton-Jacobi-Bellman equation. And let me right away mention when the dimension is equal to 1, as in this case. Now, n is either just +1 or n is just -1. And there's no tangent space to it. So this correction term zeta is just equal to 0. So this correction term is also equal to 0. So n is either just +1, which gives the supremum, and -1, which gives the infimum. So we are looking at the standard Hamilton-Jacobi-Bellman equation in that case. Now what we are looking here is these derivatives in n dimension, and we are looking at the projection into the normal direction. And we say now this is satisfied, this equation is satisfied to be equal to 0 for all tx, y is on the graph. So y is on the boundaries here. And let me note here that we have the supremum over A as usual, but we also have a direction term here. It's not only optimizing the control A, but it's also optimizing the direction zeta. So we also have to consider this optimization of the direction that we are choosing. So this is the Hamilton-Jacobi-Bellman equation here. And now we can come to the final theorem. Okay, so the theorem is, suppose let's say V is smooth, then it is the unique classical solution to the Hamilton-Jacobi-Bellman equation. And which V I'm talking about? I'm talking about this V that I defined here. So this is closed, I closed it already. So if it is smooth, if it satisfies all the regularities, then it is the unique solution to the Hamilton-Jacobi-Bellman equation. And the second part is like the verification part. Suppose the optimal arguments exists, I for txy, and zeta, the optimal direction in SS exists. Then given a y on the boundary, we have a control alpha star that is equal to y, such that alpha star is defined like this. And we have a forward going this is something obviously wrong here. Okay, no, I wanna know. That should be dxv sigma plus theta here. This should be also. Star. Okay, so it doesn't matter that much. So we have this again, the y, the same picture, so to speak, and then it goes on the surface. So we have a surface, we started with y that is equal to this, and it stays on the surface. So now what is the application that I'm talking about, the moving scalarization? Now, once we got this, we can define lambda of t of x 0t and 0x. So now we can define this capital lambda as the n at this process gamma, which is essentially equal to y actually as it moves on forward. So how do we choose this y? This y is coming from this initial problem. So when you first give me the lambda, so let's say this is my set here. So you say lambda is in this direction. So there's a corresponding y here. Let's say y of lambda. And starting from this y of lambda, now we are solving the optimization problem, and we get this alpha star, and we have this ongoing process, forward process, and we can define the capital lambda as equal to the normal direction. And it is if the set is convex, and usually it is in this case, hopefully this is convex, then wherever it comes, let's say this is the capital lambda, it is still going to be optimal. So we got this optimality in the future times immediately by setting it equal to the n, as it is going to be the optimal for this y. If it is not convex, if it gets into regions like this, well, then it's just kind of locally. So in that case, it kind of breaks out, but if the set is convex, then it is directly optimal for the future times.
So your optimality is with respect to t equal to 0, right?
Also for this problem, right? So as this moves on the surface, in the future time, this is going to be still optimal because I'm choosing this as the normal direction at that point, which this y, as it is on the boundary, is optimal in that direction, in this sense that I'm talking. So if a point is here, it is going to be optimal in this direction. So I think that's it for today. I won't mention too much for the literature. Apologies for that. Thank you very much for listening. If you have questions.
Thanks very much.